There are many applications that will involve more than two independent variables. So let's look at how we can expand what we know about partial derivatives to functions with more than two independent variables. Everything that we've used so far to find derivatives of functions with two variables will carry over to functions with three or more. But the more variables I have means I have to work with more terms in each of my derivatives and in each step of taking the derivative, and I need to pay attention to the fact that we are holding all but one variable constant each time. Consider the function f of xyz. This has three independent variables, and it means there will be three partial derivatives. There will be fx, which is defined to be the limit as h goes to 0 of f of x plus h yz minus f of xyz divided by h. There's fy, which is formally defined by the limit as h goes to 0 of f of x y plus h z minus f of xyz over h, and fz, which is formally defined as the limit as h goes to 0 of f of xy z plus h minus f of xyz over h. In general, if w is equal to a function of x sub 1, x sub 2, x sub 3, and so on up to x sub n, it means there will be n partial derivatives, and I will note them by the partial derivative of w with respect to x sub k will be given by f x sub k of x sub 1, x sub 2, x sub 3, and so on, where k is an integer between 1 and n. So now let's look at how to compute a partial derivative for a multivariable function. The key is to work carefully and keep close track of which variables are being held constant in each derivative. You'll want to work efficiently, of course, but don't be afraid to use a little bit of paper and also use parentheses to keep track of negative signs. You also want to check for common mistakes like a missing negative sign, or that you forgot to use the chain rule or the quotient rule, or something that we already know how to do very well. Let's work an example. I want to find the first partial derivatives of the following functions. The first function, f of xyz, is equal to 2x squared y minus 3x z to the fourth plus 10y to the fourth z squared. And the second function, f of wxyz, is equal to 3 times the natural log of the quantity 2w plus 5z squared minus 4w e to the x minus 2y power. For my function with three independent variables, my fx will be equal to 4xy minus 3z to the fourth. Notice that the third term in my function, 10y to the fourth z squared, has no x in it. It's all a constant, and the derivative of a constant is 0. So I only have two terms in my partial derivative with respect to x. Fy is equal to 2x squared plus 40y cubed z squared. In this case, the second term is entirely a constant, and I'm only left with two terms in my partial derivative with respect to y. Fz is equal to negative 12xz cubed plus 20y to the fourth z. In this case, the first term in my function is entirely a constant, so my partial derivative with respect to z again only contains two terms. In the second function that involves four independent variables, fw is equal to 6 divided by the quantity 2w plus 5z squared minus 4e to the x minus 2y power. I hold everything but w constant and take the derivative with respect to w of the entire function. Fx is equal to negative 4w e to the x minus 2y. There is nothing in the logarithm term that contains x, so it's only the second term that is involved in this partial derivative. Fy is given by 8w e to the x minus 2y power. I have no y in my natural log term, so that term acts as a constant and goes to 0 when I take the derivative with respect to y. Fz is equal to 30z divided by the quantity 2w plus 5z squared. In this case, the second term in my function contains no z variable, and therefore it acts entirely as a constant, and the derivative goes to 0. Here's another example. I want to find the first partial derivatives of the function f of wxyz is equal to w times the square root of x plus 2y plus 3z. Fw is equal to the square root of x plus 2y plus 3z. This is entirely acting as the constant multiplying w in my function. Fx is given by w divided by 2 times the square root of x plus 2y plus 3z. Fy is given by w over the square root of x plus 2y plus 3z, and Fz is given by 3w over 2 times the square root of x plus 2y plus 3z. Now you get to try it. Pause the video and find the first partial derivatives of the function f of xyz is equal to z times the cosine of xy plus x times the sine of yz. When you're ready, restart the video to check your understanding. We're only taking a first partial derivative, but we have to take the first partial derivative with respect to x, and the partial derivative with respect to y, and the partial derivative with respect to z. The partial derivative with respect to x, fx, is given by sine of yz minus yz times the sine of xy. Fy is equal to xz times the cosine of yz minus xz times the sine of xy. And finally, the partial derivative with respect to z, or fz, is given by the cosine of xy plus xy times the cosine of yz. This is how we can work with partial derivatives with functions of more than 2 independent variables. Be sure and let me know if you have any questions about holding variables as constants while taking the derivative with respect to a single independent variable at a time.